So I'll hit record so we don't miss anything. So welcome back. Start the party. Happy Thursday. Happy almost spring break. I put up something for you to do. You have another formative assessment available that if you can work on that before Monday night. I will let you know when your next homework is available, hopefully within the next few days, I would say. I need to reconfigure a few things, but it should be up relatively soon. And as a spoiler alert, the first section of your next homework will involve a 4-category predictor, which I am about to describe to you. So, again, not many surprises built into here. So does anyone have questions or anything that they want to talk about before we dive back into some stuff? No? Nothing springs to mind, at least? You can reserve the right to change your minds and have questions later. That's cool. So we were talking last time about how would I answer a research question involving a categorical predictor of a quantitative outcome. And I had sort of off the top of my head said it boils down to 4 steps. Step 1, make new variables that represent differences between pairs of groups. Step 2, put the new variables in the model. Step 3, figure out what else you want to know that the model hasn't told you directly and ask for it. And then what was step 4? Oh, I know, it was effect size. That's what it was. Because knowing the group differences in the units of the original variables is helpful but not sufficient for characterizing what you found. So effect sizes are a way to more generally convey the size of an effect in a metric that people readily understand. So D is an effect size for group mean differences, is what we're talking about here. R is an effect size for correlation, which works a little better for quantitative predictors. But let me see, we did most of this before. We did that stuff for 3. Do you want to see what this process would look like for 4 groups? So step 1 then, back to a new problem. What if I have 4 different groups within a predictor, or 4 categories? So for example, I have just a little worked example here, no syntax needed, but the logic of how this would work. Let's say that I have a 4-arm treatment study where I'm comparing some kind of control business as usual to 3 distinct treatments. So I hope that each of the treatments would work. I'm not sure which is going to work best, so I try out all 3. So given the interest in finding out whether or not each treatment would be effective relative to control, it would make sense to designate control as the reference group. So once you set up the model, every term in your model is going to have something to do with the reference group. That's why it matters, conceptually, which one you pick. There's no wrong choice. You can code it up any way you want. But given that the results of the model ideally are going to be answering your questions, it's helpful to set the model up in a way that's going to be most direct and informative. So when I say, for instance, make the control group the reference, what that translates to is in the new predictors you're going to create, the control group gets a 0 value across all of them. So making the control group the reference predictor, reference category, then means the intercept of the model is going to give you the predicted outcome for the control group specifically, because that's when all of the predictors are coded 0. So I have 3 new predictors that have to be created to differentiate 4 categories, and I'm calling it D1, D2, and D3, where D stands for difference. And it's 1, 2, 3 because it's treatment 1, 2, 3. So you can name these whatever you want. I encourage you to come up with names that are short, easy to type, and still meaningful. Now, could I name my predictor 1 or 2 or 3? I could not, because variable names cannot start with numbers. So that's the one limitation. And I would avoid special characters other than underscore as well. So D1, D2, and D3 are the new predictors that I'm going to create. And why do I need to do this in the first place? What would happen if I took this original treatment group variable and I put it into the model as is? So this first column right here, this variable, if I put that into the model as a predictor, what would happen? Would my program say, wait, you're doing something stupid, stop it? Or would it be like, okay, here's your results?
I assume the second one.
Yeah. SAS is like, no problem, here you go. Here's your slope. So that's a Q. Slope, singular. It would fit a slope, giving me the difference between control and treatment 1. That would be forced to be the same as the difference between treatment 1 and 2. That would be forced to be the same as treatment 2 and 3, because it'd be a line. It would be a line through this variable thinking that these are numbers. A linear slope is what I would get. And that's going to make no kind of sense for something like this. So this is a nominal variable where the categories are not ordered. Control versus each of the treatments is sort of ordered, but there's not necessarily an order amongst these latter categories. So you want to be careful not to put in the original predictor, especially when the predictor is not really a number. This is why we have to go through this coding scheme so that we have 0 versus 1 as a variable that will separate out each of our 4 possible categories. So control versus treatment 1 is going to be given by the slope of D1. Control versus treatment 2 is going to be given by the slope of D2. And control versus treatment 3 is given by the slope of D3. Okay, with me so far? Zoomers, see a few faces, few thumbs, excellent. So here's my model. By the way, what is this called again? When I have a categorical predictor of a quantitative outcome, what does the rest of the world call this type of model? This is ANOVA, yeah. ANOVA is a special case of a general linear model where you have a 3 or more group predictor and a quantitative outcome. So here's my model. The model is going to tell us how each group differs from each other, as well as what the predicted outcome is for each group. Some of those quantities are going to be directly given and some are going to be indirect. So first off, how does the model tell us what the predicted outcome is for each kind of person, for each group in this case? Well, beta 0 is my fixed intercept. Beta 0 is always the expected outcome when my predictors are 0. Given the way that I set this up, so that the control group is the one that's zeroed out all the way across, beta 0 is going to be my predicted outcome specifically for the control group. The predicted outcome for each of the other groups is then going to start with beta 0 and then pick up the effect of the slope that differentiates each other group from control. So beta 0 plus beta 1 times D1 is how I'm going to get the mean for treatment 1, because D1 kicks on, so to speak, when treatment 1 is what we're talking about. And D2 and D3 stay 0 if we're talking about treatment 1, so they don't go into the prediction. They zero out. Same exact idea for the treatment 2 mean and the treatment 3 mean. They each start with beta 0, and then they pick up the added effect of being in that separate group via the slope. So D2 kicks on to activate beta 2, and D3 kicks on to activate beta 3. So you can kind of think of these as switches. So in this 4-group scenario, I have 4 fixed effects. I'm going to get one of the means, and I'm going to get 3 of the potential mean differences directly. So let's say that I know the right answer for what the model parameters are going to tell me because I ran the means. I did like proc means by group, or summarize in stata by group, or what's it called in R? Describe by group, describe by actually. And let's say that the control group's mean is 10, the treatment 1's mean is 12, so they did a little better. Treatment 2's mean is 15, a little better yet, and treatment 3's mean is 19. So it looks like treatment 3 is the best, if the outcome having more is a good thing. Let's go with that. So given that the model tells us how these means are formed, it also necessarily tells us how the groups differ from each other. So control versus treatment 1, the alt group, so the one that's not the reference, treatment 1 in this case, is beta 0 plus beta 1. The ref group is control, and its mean is given only by beta 0. These two beta zeros drop, and I'm left with just beta 1. And based on the pattern of means, beta 1 has to be a positive 2, because treatment 1's mean is 2 more than the control group's mean. If I had treatment 1 doing worse, let's say that the treatment actually backfired, then this slope would be a negative number, because treatment 1 would be lower than control in that case. Likewise, control versus treatment 2. The alternative group is beta 0 plus beta 2 minus just the beta 0 part, so beta 2 must be 5, because the treatment 2 group is 5 more than the control group. So the slopes of these new dummy-coded predictor variables that we've made are group differences relative to control. When you're dealing with a binary variable like this, let me go back to what the variables look like here. The slopes always tell you how the one group differs from the 0 group. And I'm saying that very deliberately because that's an answer to like 6 different homework questions. The slope always tells you how the one group differs than the 0 group. Same thing for treatment 3. So each of the slopes then tells us how the alternative group that is targeted by that predictor differs from control. And in this numeric example, all the differences are positive because treatment was effective relative to control in each case. So we've done step 1, which is make the variables. Step 2, throw them in the model, and then we'll be ready for step 3 after I answer this question.
A clarifying question, are the 2, 5, and 9 the slopes then?
Mm-hmm.
Okay, thank you.
Yep, 2, 5, and 9 are the slopes because they are the change in the outcome for a 1 unit change in the predictor.
Right.
A 1 unit change is moving from the 0 group to the 1 group.
Perfect, thank you.
Yep. So these are slopes in the same way that we talked about slopes for quantitative variables. It's just that they are slopes of a variable that can only be 0 or 1. Mm-hmm. A binary predictor. Okay, so made the variables, put them in the model. Now you have the rest of the slide in front of you, which sort of spoils the surprise, but can you imagine something else that you might want to know about these results?
The difference between the treatment.
Yeah, which treatment worked best? I don't know that yet. None of the model parameters that I am directly given, beta 0, beta 1, beta 2, beta 3, tell me that. But I can figure it out because the model does give me a separate mean for each group, therefore it has to give me all of the other mean differences as linear combinations. So this is step 3. Figure out what else you want to know and ask for it. So generally speaking, with this type of dummy-coded indicator coding system, any difference among the not reference groups is something you're going to have to ask for. The model parameters are all oriented towards the reference group, what its mean is and how it differs, or the other groups differ from it, I should say, as a reference. So this same logic of how we got the differences for the first 3 works to get the differences between the alternative groups. So if I have an alternative group of treatment 2 minus the mean for treatment 1 as my reference, then it's beta 2 minus beta 1 is the thing that I need to ask SAS, Stata, or R to do for me. Now I can look at these numbers and be like, well, I know what the difference is of beta 2 minus beta 1, it's 3. Well, that's cool, but is that significant? I don't know. What do I need to know if 3 is significant?
The effect?
The effect, keep talking. This is the estimate of the difference. What else goes next to the estimate? Standard error, yeah. Yes, standard error, expected inconsistency. So I need to ask the program to do this math for me to get the standard error. And yes, you can compute standard errors by hand with a calculator if you want to, but at that point, just stop. Because even if you're super duper careful, if you're working with output that's a summary, it may not be sufficiently precise to actually get the answer right. So computers are better and faster and more accurate. So anytime you find yourself trying to do something by hand, just stop and try to find a way to do it within the program with the results directly. This is something that I did not learn until I was on the tenure track. And then I was like, oh my God, I could have used this so much earlier. So I start with this because asking it to figure out how to get extra things out of the model that are in there, but they're just not explicit, is a really useful strategy. So the same thing then if I want T1 versus T3, I have what the model is, what the model says the mean is for the treatment group 3, minus what the model says it is for treatment group 1, and the difference is 7. So it's beta 3 minus beta 1. So in the programming statements, the slope that is to be subtracted would get a -1 next to it, and the slope that is to be not subtracted, the one that starts with, gets a regular 1. So in these sorts of statements, like here's what it looks like in R. So this is a difference between two alternative groups to get middle versus upper in our previous example. The slope that differentiates low from middle gets the -1. The slope that differentiates low from upper gets the 1. So this works out to be this slope minus that one, if you put the -1s and 1s in there. So it's sort of untransparent in R. It's much more transparent in the other packages, especially Stata. So in Stata, the corresponding statement would look like this, where the slope that you want to subtract is given the -1, the slope that you want to not subtract is given the 1. And then in SAS, the coefficients just go next to the slopes. And you'll get a chance to practice this in your next homework. So I'm not giving you the code for a 4-group example. I gave you the code for a 3-group, and I'm asking you to adapt it. But this is the logic that will work in terms of following it. And I'm happy to answer questions as the process unfolds. But that's not this week, that's next week. Okay. So how are we doing with this? Ish.
So a 4 category is 3 treatments and a control.
As an example.
Okay.
There's probably lots of other 4 category examples out in the world. And it's up to you which one you designate as a reference group relative to the others. The way that I learned how to do this, by the way, so these sorts of linear combination statements I didn't learn how to do. The way that I learned how to do it is to re-estimate the model, changing the coding scheme. So like if I wanted to know about treatment 1 versus each of the others, I would redo the model, making that treatment the 0, and then all the slopes that I get out of the model would be for that one. And then I'd do it again for treatment 2. So I'd have to estimate the same model 3 different ways to get all the pieces of information. And that is unnecessarily confusing. So it's all in there. You just have to know how to ask for it.
And then you said when you answered my question earlier that 2, 5, and 9 are the slopes. Are those fixed slopes?
Yes, they are.
Okay.
And the term fixed is probably not something that shows up in the textbook, but I use it because it's differentiating what you will later learn about as random slopes, where what fixed means is that is a constant. So it is an estimated constant, like 2 is the difference for everybody, as opposed to a variable, which is a whole different kind of model, known as random effects models. So these are fixed effects. So in general, as long as you have as many fixed effects as you have categories, each category will get its mean recreated exactly, and you'll be able to get differences among any of the categories that you want. So then step 4 would be to get effect sizes for each of these that describe in a standardized way how different each of these groups are. Because the meaning of these numbers is tied to the scale of the outcome specifically. So I don't know, unless I understand this study and how the outcome was measured, if 2 is a lot. And just finding out that 2 was significant or not doesn't answer that question. Because 2 could be significant because I have a whole bunch of people, or because it's a really big effect. So effect size helps to delineate which of those possibilities is responsible for a significant result, or both. Okay, questions? So let's say that I put my 4-category predictor into a model, and the residuals get smaller. So you had a question on your homework about this last time, the idea of the residuals shrinking. Now, do I know, based on the results of just each of these differences, which set of group differences is responsible for shrinking my residuals? I don't. Yeah. So that's what we have to do next is, okay, how do we talk about the joint effect of this idea of group when group is characterized by 3 different slopes at the same time? We need some way of lumping it back together again so that we can have sort of a joint, omnibus, overall, how effective is group at reducing variability? So that's where we're headed next. So back to the 3-group example, because that's the one that I have syntax and output for. So I'm on page 11 of the slides here. So in this example, we had annual income predicted by self-reported working class, where people could choose low, middle, or upper. And for those 3 groups, I only need 2 slopes. So the model looked like this. So research questions that lend themselves to this type of analysis is, does group membership predict Y? Or are there significant group mean differences in Y? Well, I can figure out for each pair of groups what happened. So for this type of model, if beta 0 is significantly different than 0, then that means the mean for low is different than the mean for middle, because that's how I created this variable. And if beta 2 is significantly different than 0, then that means that upper differs from low. And if the difference of the 2 slopes, so beta 2 minus beta 1, something I have to ask for specifically, is different than 0, then I know that the non-reference groups, middle and upper, also differ. But I don't yet have an answer to this overall question: how important is this grouping variable in the grander scheme of things? To do that requires a joint test of beta 1 and beta 2 at the same time. And to do that, we need to meet a new letter. So the new letter, I feel like I'm on Sesame Street. Today's lecture is brought to you by the letter F. And no, F does not stand for what you might think it stands for when you think of statistics class. It stands for something else. But it's the new letter F to add to our collection of letters. So T and Z and R and D, now we have an F. And it's always capital F, by the way. I know. So another way of phrasing the same question is, do beta 2 and beta 1 work together? Is the variance of the residuals, so the e's at the end of this equation here, is it significantly smaller because of these 2 slopes? That's one way to think about it. Another way to think about it is, okay, so this model gives us a predicted outcome for 3 different kinds of people. Is that predicted outcome significantly related to the real one? Did the prediction work? So that's 3 different ways of describing the same phenomenon. Do beta 1 and beta 2 work together jointly? Do the effects of beta 1 and beta 2 on the residuals make the residual variance smaller? And does the outcome that's predicted by this model correlate significantly with the real one? So what we have to talk about then is a way to answer all of those questions. One question. And the answer in this class lies in degrees of freedom, sums of squares, and mean squares. Now, do those words mean anything to you yet? Are these terms you may have heard before? Maybe? Okay, they're coming back then. So a more general answer requires us to lump together beta 1 and beta 2 and ask whether their joint contribution to the model is significant. This is your first example of something that is known more generally as a multivariate wald test. So we'll have several examples of this throughout the semester. And we have to quantify how good our model is relative to what we still don't know, and how many terms we had to add to get to our current level of prediction. So everything is relative in this case. So relative with respect to how many slopes did we have to add to get to this level of prediction is what's going to be known as numerator degrees of freedom. So in this case, it's k minus 1 because we don't count the intercept. The intercept is even in the empty model. It doesn't help us predict anything. It just lets the mean of y be different than 0. So numerator degrees of freedom, new vocabulary word, number of slopes in your model. So beta 1 and beta 2 together give me numerator degrees of freedom of 2. Denominator degrees of freedom is how many slopes I could still add if I wanted to. Not yet spent. And that's a function of sample size. So if I wanted to have the most perfect model ever, and I have 734 people, I could put in 733 slopes, and it would perfectly predict the outcome. I could put in a slope for each person. Slope for you, slope for you, slope for you, slope for you, you. 733 of them, be perfect. Now, giving each person their own slope is maybe not useful, because I don't know why, your slope's different than my slope, but I know that it is. So denominator degrees of freedom is this sort of idea of potential, how much more complicated could we make this model relative to what we've already put in. So degrees of freedom you can think of as money or points. This reminds me sort of Weight Watchers points. The dieting thing where you're allocated so many points, and if you eat celery, that's no points, and if you eat a pizza, that's 30 points, and it's up to you how you allocate your food. Back in the 1980s, this was called Deal-A-Meal when it was invented by Richard Simmons. He had a wallet that had food cards, and you open your day with the wallet, and every time you eat something, you move a food card over to the other panel, and when you're out of cards, you shut the refrigerator and you don't come back. So this is kind of the same system. It's okay, how many points do we have to spend to get to this level of prediction, and how many do we have left over? We got to know that in order to articulate how good our model is doing. Then the second part of it we have to articulate is, okay, how good of a job did we do? And that is indexed by a quantity that is referred to as sums of squares. And you have already seen this because it's the numerator part of the formula for variance. How far off each person's actual outcome is from the mean, square that deviation to keep the positives and negatives from canceling, and sum across persons. That's sums of squares. So that's the total. Sums of squares you can think of as the amount of information in your outcome. So we want to calculate how much information has been captured by our model, how much information is left over, how many slopes did it take to capture that information, and how many more slopes could we add that are still left over. So it's 4 ideas that go into what's going to end up with one number at the end of this. So then, how much information did we get relative to how many slopes? That is going to be what's known as model sums of squares. So how much information in our outcome did our slopes capture? So y hat is what's in the front of this thing, because that is the predicted outcome minus the mean. Now, why is it that way? Think about this. If I had a truly crappy model, I had a bunch of predictors in there that had no relationship with the outcome, then the predicted outcome would probably be pretty close to the mean outcome. Because if I don't know anything else, right, the slope is flat, everybody gets the mean, and to the extent that my predictor is useful, the slope is not flat, which means the prediction is different than just the flat line mean prediction. So this is like an index of how much additional information is in our prediction relative to a naive baseline of just the mean for everybody. So we take that, square it, sum it across people, and then we divide it by the number of slopes that it took to get to that level of prediction. So number of fixed effects minus 1 works out to be number of slopes because the minus 1 is for the intercept. And that ratio has a name. It's called mean squares for the model, because this is like an average. So putting all of that together, this quantity of mean square for the model is like how much information did we capture in our outcome per slope spent to capture it. So it's a per slope estimate. Okay. Then the rest of it, how much is left? Our model's not going to be perfect, we know that. How far off are we? So we first need to figure out the deviation between what y actually was for each person, which is the y sub I here, minus y hat. That's what is known as E most of the time in our equation. E is how far off your actual outcome is from the one that's predicted. That's your residual. So we take these offnesses, we square them, sum over persons, and then we divide by the number of slopes that we could still add if we wanted to. And that's denominator degrees of freedom. So then we end up with a very similar type of ratio, and this is mean square residual, or mean square error, depending on your software. And that is how much information is left over per slope that you could have added but didn't. And all of it gets summarized in this handy-dandy table. So if you use SAS or Stata, you will get a table that looks very much like this one. R separates this table into multiple chunks and prints it out differently. But all three packages will give you all of this information. So this is all very abstract. Can I give you a real-world analogy that might help? Okay, so I'm going to talk about my mom. My mom and I do not agree on a lot of things. We don't fight, but we just don't view the world in the same way. But the one thing that we agree on is that we love Kohl's, the department store. At home, I am pretty much in Kohl's tech gear, which is like their off-brand Nike stuff, like head to toe every day of the week. Like I live in the Kohl's tech gear line. And my mom loves Kohl's. And at Kohl's, if you pay full price for something, you are doing it wrong. There is never a reason to pay full price at Kohl's because there's Kohl's Cash, everything's on sale, there's extra like sales that happen on Thursday through Sunday, there's Family Day, you know, there's savings on holidays. Like you're doing it wrong if you pay full price at Kohl's, let's just say that. So I already have an expectation of getting a good deal at Kohl's because they have all these gimmicks that are designed to make you, go and shop there. But if my mom calls me up and she says, Lisa, you'll never believe what a great deal I got at Kohl's today, I know that this exceeds my normal expectations for how good of a deal I can get at Kohl's. So if she's going to articulate to me what made this such a great deal, she has to tell me two things. How much money did she spend, right? And what did she get for the money? So she usually starts with, I only spent $7. And then I got a shirt for me, and I bought a new pair of pants for Huey that I found on clearance, and then I got your dad some socks, and then she goes through the list of all the things she buys, right? But it's $7, right? That's what made it a good deal, is that she got so many things. I got a good deal because I only spent $7 and I got all this stuff, is mean square model. What did you get? How many things did you get, and how much money did it take to get those things? So money spent is like numerator degrees of freedom here. How many slopes did it take to capture this information? How much money did you have to spend? And then how much information did you get with your model? Is like, what's your loot? That's mean square model. It's only a good deal if you, per item, have a very low price. Like if I spent $50 on a shirt at Kohl's, that's going to blow the whole scale of things, because then it's like, well, if I spent $3 on a pair of socks but $50 on a pair of a shirt, then like that is not a good average across the two. So it's like per dollar spent. That's mean square model. But then what indexes it as being an exceptionally good deal is the price of everything that would be left at the store that you didn't buy. So all the money you could have spent is like denominator degrees of freedom. And all the stuff you didn't buy is like sums of squares residual. So model is like what you got, how many slopes did it take to get that level of prediction. Residual is, okay, what information is still left in this outcome yet to be accounted for, and how many more slopes could you have added? And what quantifies a good deal in this class, our friend F, is that the mean square for the model should exceed the mean square for the residual. Otherwise, it's not a good deal. So the ratio of those two things is going to form a new test statistic known as F, capital F. Mean square model over mean square residual is going to be given to you as something called F. Okay, how are we doing so far? Now it's a new set of vocabulary and new concepts.
You said that the MS model needs to be greater than the MS residual,
That's right.
and then it's a good deal.
Mm-hmm.
And
Then it's a good deal.
when you talk about the K, can you remind me what that means?
K is the number of fixed effects,
Okay,
and it's -1 because we don't count the intercept, so it boils down to number of slopes.
okay. And then when you talk about how many slopes we could have used, or could have made,
Yeah.
how do we know that?
It's based on sample size.
Okay, okay.
So you can have as many slopes as you have people -1 because you have to have an
gotcha.
intercept.
I knew that, I'm sorry.
No, that's okay. It's good to review because this is where like the letters, right? You got to have them at the top of your head for this to make sense. N is sample size, K is number of fixed effects. Y hat is the Y that's predicted by the model. Y bar is the mean. Y sub I is the original outcome. And so it's like it's carving up the total variability into two chunks. That what we know because of the model versus that what we don't know that's left over. That's still an E. Okay, question. N minus K is what you did not spend. Yes, we did not spend it. And SS residual is what is left at Kohl's. Yes. SS residual is the rest of the store. SS model is your shopping bag. And it's only a good deal if you paid less for the things in your bag than you would expect to pay generally at the store. It works. Takes a little bit of massaging to make it a story, but it works. Another question, is the value of the slope taken into account using the same example, a certain brand over another one, or a vacuum cleaner versus socks? Yeah. So the bigger the slope, the larger the effect size, the more information has been captured by your model, the bigger your shopping bag. And I'm using the word information because sums of squares is like, what the hell is that? And I can't say variance because variance is sums of squares divided by a denominator. So I'm using the word information captured for sums of squares model. Information left over is sums of squared residual. Point spent to get your information is degrees of freedom for the numerator. Point remaining is degrees of freedom for the denominator. So MS residual, do you remember in your first homework I told you to look for that number? And I said, we'll ignore the rest of the table for now. This is the now. What is this thing? Otherwise known as? I introduced a label for this before I introduced the table. What is mean square residual or mean square error, otherwise known as?
Is that the F?
It's not the F. It's the denominator of the F, so it's related. Otherwise known as the first question I asked about each model to be fitted in your homework. And I told you that if you had this number right, it meant you had the contents of your model correct. Two-word phrase, first word starts with an R, second word starts with a V.
Residual variance.
Residual variance, yep, ding ding. Yep, residual variable or residual variance, I'll take it. That's mean square residual. Because it's information left over divided by how many slopes we could have added. So it's in a variance metric. And if I took the square root of this number, it would tell me how far off my prediction is on average for each person. Like, what's the average E, so to speak? This is like your average E squared. So in an empty model, it's mean square total is what you get back because you haven't explained anything. An empty model just has an intercept. And then once you start adding predictors, then the total variation in your outcome is split into two kinds, explained and not explained. Explained is model, not explained is residual or error. So this quantity right here, variance explained by the model fixed slopes, this is R square. That doesn't count as a new letter though, because we have R. And do you know how R and R square relate to each other? Don't think too hard.
It's squared.
It's squared, yeah, exactly. But for whatever reason, once you square it, it becomes capital. It just does. I didn't make it up, but this is how the world talks about it. And yeah, R square is R squared. So it's not new. But what it refers to, you can think of two different ways, and they're both correct. Algorithmically, how we get R square is sums of squares total, which is like the total amount of information in your outcome variable, minus sums of squares residual, which is the amount of information left over after doing your model, divided by total that there was to start with. So this is interpreted as a proportion. It is the proportion of total variability your model has explained. So if my R square is 0.2, then I would say that my model has captured 20% of the variance in my outcome, and there's 80% left over that I don't know why. If R square were 0.9, then I've captured 90% of my outcome variance, and the data must be simulated because that never happens in real life. At least not with studies with people in social sciences. Then there's 10% left over. So you can think of it that way. R squared tells you what proportion of the total variance your model has captured. And you can also think of it by referring to the concept of R as a correlation. I can take the y hat that's predicted for each person and literally make it a column in my data set. Every software package will do this for you. So I can save what the model says y should be for each person in my sample as a column. I can take the original column for y, and I can ask it to run a correlation between those two columns. That's R. And if I want to turn it into an R square, I square it. So you can also think of R square as the square of the correlation between the model predicted outcome and the real outcome. And just like R is an effect size, R square is an effect size. F is the test statistic that goes with R square. So just like we had a slope estimate and a test statistic for the slope that gives us a p-value as to whether the slope is significant or not, but then we still need an effect size for how big the slope really is. This is the exact same set of concepts, but now talking about the contribution of the slopes together in a model when there's more than one slope. So F tells me whether or not the slopes work together significantly to predict y, and R squared tells me how good they did at predicting y as an effect size.
Can you repeat that one more time, please?
Yes, happy to. F tells me whether or not my slopes work together significantly to predict my outcome. And R square tells me how good a job they did at predicting the outcome. So if F is significant, you got a good deal. How good a deal was it? That's R square. So what's potentially confusing about this is the use of squares for some things and not others. Squares generally are used to keep positive and negative numbers from canceling. So if I want to lump together two slopes, for instance, in this example, and test whether the two slopes work together, I don't want the slopes canceling each other out if one's positive and one's negative. So working in a squared metric prevents that from happening. And T, as a distribution, looks like the normal hump, right? It's symmetric and it goes in both directions. F, because it's a squared concept, is not. It looks like this. So here are a couple examples of F distributions that I stole from various places, linked below. And to know where 5% unexpected starts in F, because that's still going to be our standard for what significance means, is that it would be expected less than 5% of the time if the null hypothesis were true. To know where that 5% starts in F, you have to know two things. So the numbers that are in the parentheses here, these are degrees of freedom. The first number is always degrees of freedom for the numerator, number of slopes. So number of slopes is first, degrees of freedom numerator, comma, and then number of slopes you could have added but didn't, denominator degrees of freedom, which is based on your sample size. So for instance, if I look at the top left corner, if I have 4 slopes in my model and I could have added 12 more, That's a very small sample, by the way, because that would be n minus k is the 12. That would be a total of 17 people. Because I have an intercept and 4 slopes and then 12 left over. That gives me back to n of 17. So if this is my situation, then I have to have an f greater than 3.26 because that's where 5% starts out here in this tail. So f doesn't go negative. The smallest f can be a 0. So f is always going to be a positive number. If I have 10 slopes and 100 slopes left over I could have added, then the critical value of f for where 5% starts is 1.93. So the same is true. The more people you have, the easier it is to say that f is significant. Where unexpected starts moves in closer to 0. So the general concept here is doing a significance test for how good the model works. And F is a test statistic that lumps together the contributions of individual model predictors so that we can answer that question. What's next? Okay, summaries next. That's probably a good call. How are we doing? Hit me.
I'm wondering about the purpose of the f value because I'm considering the difference between p-value and f value because p-value tells us the differences between how significant between the two groups.
Mm-hmm.
But what's the difference between the f and p-value and what's the purpose of the p-value, f value?
Okay, so the question was, how are P and F different?
Yeah.
So P stands for probability. And every test statistic has a p-value associated with it. So if we're testing one slope, then we use t, and we can get a p-value that is the area that corresponds to where t is on a t distribution. The same is true of f.
So f is about the model?
F is a test statistic. F is a way of standardizing how good our model did relative to how complicated the model had to be that good. So it's F is information explained over number of slopes it took to get it. That is like numerator, that's mean square model. And then denominator is information left over divided by how many slopes I could have added but didn't. And that's mean square error, mean square residual. So if I did good, F should be greater than 1. If I added a slope and it did sort of as well as to be expected just based on chance, then what my model did and what's left over should be on equal footing and F will be 1. So you will have a p-value with every single test statistic that you compute for something. And there's 4 possibilities that you'll see most commonly. And that's actually on the next slide, so maybe that would be a good segue to do that. But other questions? Okay, let's do that. Let's do a little review. So the idea of significance testing. We're trying to make a binary decision as to whether or not we're going to label a result sufficiently unexpected relative to the null hypothesis. So we have to decide several things a priori. Alpha. Where does unexpected start? What % of the time are you willing to live with a result that is still possible, but unlikely if the null hypothesis is true? Alpha is also known as your type 1 error rate. So if the null hypothesis is true, for instance, if the true slope in the population is 0, then I would see a slope this big, less than 5% of the time. Okay, that's sufficiently unexpected for me. But I am going to be wrong 5% of the time. So we have to choose alpha ahead of time. 0.05 for alpha is the common standard. If you want to be conservative, you make alpha smaller or bigger if you want to be conservative. Smaller. You want to make the standard for unexpected harder to reach. Like 1% of the time you would see a slope this big. That means that you're only going to have a false positive type 1 error 1 time out of 100 rather than 5 times out of 100. If you want to make sure you don't miss anything, right? Anti-conservative, as they sometimes say, or lenient, then you would make alpha higher. Well, I don't want to miss anything, so I'm going to say 10% is where unexpected starts. That's alpha of 0.1 instead. And then, am I willing to be wrong in either direction? That corresponds to whether we're using a one-tailed test or a two-tailed test. And as you may recall, I think one-tailed tests in most cases are bullshit voodoo, and we're not going to do them. Because if I think there's no effect as a null hypothesis, I'm willing to say there is an effect if it's significantly positive or significantly negative. I might have like a theory as to which I'd prefer, but I'm willing to say that both are equally plausible. So then I allocate my area to both sides, basically, of where 5% is. 2.5 over here, 2.5 over here. So then what your test statistic is to answer that question of whether something is significant or not boils down to 2 dimensions. If you're testing one slope or if you're testing more than one slope. So if I want to know, for instance, if there's a difference between control and treatment, one slope, I do that with t because I want to pay attention to my sample size because I don't want to screw things up by ignoring sample size. If I have a sufficiently large sample, or I have known population variances and other things that very rarely happen, then I would use z instead. T with a big enough sample size becomes z. So that's why it's always t, because it doesn't really matter at some point. It matters if you have small samples. So t is sort of baked into all the software for general linear models. So that's for testing one thing. And if you have a t or a z, it's computed as estimate divided by standard error. The only difference is the reference distribution for where 5% starts. So up to this point, we've really only talked about t because that's all we've needed. Now we're introducing the second column here as a possibility. How do I assess the significance of more than one slope at a time? So if I have 3 groups, it takes 2 slopes to differentiate the means in the 3 groups. If I want to know if group as a concept is a significant predictor, that's a 2-slope question. I need f to do that. So f is for lumping slopes together to get a joint test for them. And if I only have one slope, t squared is f. It's the same thing. And that's why I told you in homework 2 that you could ignore the rest of that whole table. Because you only had one slope in homework 2. So if that slope's t is significant, you can be certain that the model's f is significant because it's literally telling you the same thing. T squared is f if you have one slope. From this point forward, though, we will have more than one slope in all of our models. And so to ask about their contribution jointly, we need f. And if you're like, I have enough people, it doesn't matter, then f becomes chi-square. So that's another stat that you may see for certain things, such as a chi-square test of independence for categorical variables, like a crosstabs thingy. You may have done that in intro stat. It shows up in advanced classes quite a bit for comparing the relative contribution of one model versus another model. But for our class, we're going to pretty much be in T and F. So then to answer your question, like where does P fall into all of this? There is a P value that goes with all 4 of these. Each has its own. because P is a probability of something happening, and it's relative to what is expected given this distribution. So T is two-sided and symmetric and kind of squatty, and it gets tighter as you get more people and becomes Z, excuse me. F is this one, and it eventually, chi-square looks like chi-square after a certain point, but it's asymmetric. So the probability of something happening only is on this side of it, because F can only be positive, because it's a squared metric. But it has a probability associated with how often you'd see an F that big if the two slopes in the population, or the four slopes in this picture, did not have a significant contribution. So for all four of these things, if the test statistic exceeds the distribution's critical value, meaning the boundaries where alpha starts, like where the 5% mark is, then your p-value is going to be less than alpha. Then the language goes, we reject the null hypothesis. It is sufficiently unexpected to find a result this far away from the null, so we're going to call it significant. The alternative, if we don't cross that 5% magical boundary, if P is greater than or equal to alpha, meaning that we're within expected territory, then we do not reject the null hypothesis, or we retain. Someone can yell at me, but to me those are synonyms. The one thing you can't say is accept. That one you will get yelled at for. You cannot accept the null. But what we're saying is, yeah, this could have happened just from random fluctuation. This result is well within expected territory, so the result is not significant. So this thumbs up, thumbs down significance decision is made in all four of these distributions. They're just used for different purposes. T is for testing one slope at a time. F is for testing more than one slope. Yeah. Okay. So then the words that I said before, I had written down here. Why didn't we have to pay attention to this in homework 2? Because if you have only one slope, the test of that slope is the same as the test of the model. So one slope model that looks like this. This would be appropriate if you have a quantitative predictor that you're happy with having only a linear relationship captured by beta 1, or if you have a binary predictor in which there's only one possible difference. So in this case, the test statistic for T is the slope's estimate minus the null hypothesis, usually 0, divided by its standard error. So T tells you how many standard errors away from the null hypothesis your result is. I can compute an effect size for the beta 1 slope in an R metric, and if I square that R, can you guess what it becomes? R squared, exactly, for the model. So if beta 1 is a significant slope via the T test statistic, then its F is also significant to the exact same degree because T squared is F. And the R effect size for that slope, if I square it, would be the model R squared. So in our current situation, we have two slopes. We can't just look at the T for either of them and talk about the model as a whole, because those two slopes create three different differences, and the model could be significant for any one of them, or all three. So here are the numbers that go with our example. So this is predicting annual income from 3-class low, medium versus upper. And the results that we skipped over, which we'll look at the next time we open up the example, This model has an R-square of 0.1. So what does that tell me right there? This much. R-square of 0.1 means 10% something.
Is it related? 10% is related to the.
10% related to, yep. Yep, okay, you want to phone a friend? 10% related to something.
Hot potato.
Exactly.
Population?
What is it?
Population.
We don't know what the population is. We're working with what happened in the sample. In theory, we hope that it applies to a population, but that doesn't change the answer to the question. 10% is something. That's where we're at here. Explaining, yep. Yeah, so this model, by putting in these two slopes, I have captured, explained 10% of the total, what? What's my like denominator for this R-square idea?
Residual?
Close, yeah. Residual is the leftover part. Total variance, yeah. So of the total variance in the outcome variable, which in this story is annual income. So of all the reasons why some people make more bank than other people, 10% of that is associated with this variable that I put in my model via two slopes. So the empty model with no predictors tells us how much variance we had to start with. And this tells us by how much that variance shrunk after putting in predictors. So if it's 10% explained, how much is unexplained? 90, yeah, most of it.
So does that mean it's not good?
It's 10% good.
Okay.
Now we could ask, is that different than 0?
Right.
And that's where the rest of the table shows up. So the rest of this gives me a significance test for that R-square. And the big number to look at here is out here, our friend F of 42. So sums of squares for the model, information captured by our predictors, degrees of freedom numerator, how many slopes did it take to capture that information? Divide sums of squares by degrees of freedom for the numerator, that's mean square model. So this is kind of like variance explained, but it's per slope. So I like to think of it as information captured per slope. Then what's left? So y minus y hat, that is E that's in here. What don't we know? That is this much information, sums of squares residual, divided by how many more slopes could we have added? Sample size minus number of fixed effects. And then mean square residual, that's residual variance. So that's the variability across people of the E residuals. The squared average offness from our model. And the ratio of mean square model to mean square residual is F, which is the 42. So that's very good, actually. That's a very strong F, because 1 would be like F of chance. And you will also get, next to F, a p-value that tells you if in the population the two slopes together created an R-square of 0, how often would you see an F of 42? Not very often. So it's way out in the tail. 312, my goodness. Time flies when you're talking sums of squares. Said no one ever, except me. So this bolded thing right here, memorize this, because you're going to complete your homework with this sentence like 87 times by the end of the semester, where you have to pick the drop-down menu that corresponds to these numbers, because the entire world has agreed on one way of reporting this information. F, degrees of freedom, equals the F that you got. Mean square error equals the residual variance, and then P. And then you'll have probably one more drop down with another comma that gives you R square, that ties this whole thing together. And the reason that people report these particular values is because if you have these values, you can reconstruct this entire table by working backwards. If I have F and I have mean square residual, then I can figure out what mean square model must have been. And if I have mean square model and I have degrees of freedom, then I can figure out what sums of squares must have been. So they can work backward to get all the missing pieces just from what's included in this right here. All right, questions before we call it a week, not just a day. No? Going once? Going twice? Okay, no more questions? I hope everything goes well for you with respect to midterms and whatever else you're facing. If you get a chance, please do your formative assessment by Monday night so we can talk about it on Tuesday. Cool?
Thank you.
All right, thank you. Bye, folks. Thanks for being here.
Thank you.